a few questions. How do you know about the C60? About the C60 plus interpretation of the DIBs. What fraction of the diffuse interstellar bands are identified now?
I think these three lines. Xander may have more to say about this.
I think that's
yeah. I think it's only this is the one. I think absolutely convincing identification, and I believe at this point there are no others. It's very likely that the carriers of many of the others are the same sorts of large carbon molecules, but.
Nick?
So ARH plus has been discovered. Has there been searches for like neon, NEH plus? Is there any?
I think some of our Herschel data covered neon hydride plus. Yeah, we actually addressed that in the paper, I think, again with simple chemical models and knowledge of some of the reaction rates. It can be explained why the neon H plus isn't as abundant. The argon H plus is special because there is a formation reaction that goes at low temperature, and the same is not true with the neon H plus. I think the best place for looking for that and also for HEH plus might be in the molecular tori around AGN, where there might be molecular hydrogen exposed to such a high ionization rate that the reactions involving H2 plus would drive the formation of those molecules, but we don't see them in the general interstellar medium. The chemical formation rates are not fast enough.
Thank you. Let's thank the speaker again. I'm afraid we have time. They're using the really good the same computer, so we should be able to make a quick transition. He said, our next speaker, again, needs no introductions. Xander Tielens from Leiden. And I really feel lucky to be here this morning to hear these two giants in the field hold forth. The floor is yours.
Thank you, Bob. That's very kind. I was given the charge to talk about molecules in PDRs. I actually changed the title slightly to talk about the largest molecules and also the largest atoms in PDRs. But before I go and try to explain why, let me go down memory lane to this one paper that I share with Gary. It goes back to the mid-90s, and to be honest, I had completely forgotten about it. I'm not even sure that I knew about it. I think this is a case of quantum entanglement. I think what happened is that I was walking around at the NASA Ames, walked by Bob Rubin's office and admired his newest addition to the Orion display that he has. And at some bizarre reason, I got entangled into this paper. It's actually a very interesting paper, and I wish I had actually read it or remembered it. So I have never really worked with Gary. I've never really worked with Cloudy. You know, I'm not a modeler kind of guy anymore, but all of my students have. And I think that's true for many, many students nowadays in this field. So let me take you from what we have been discussing for the last couple of days to where I want to go. We have been talking about this low-density plasma ionized by some central stars, producing a recombination and a cooling glow that we see here in the optical. And that has been the focus. And it has been the focus because it's in the optical. When you look in the optical, these regions are dominated by the plasma emission. But if we had molecular eyes, this region would look very, very different. And that's very clear in this particular image. This is the IRAC emission of the same region. You recognize here the Huygens region with the trapezium, but you now see all this red glow that's due to large polycyclic aromatic hydrocarbon molecules, which are glowing because they're being pumped by the UV light from these central stars. And this is on the scale of a nearby region of massive star formation, but we can go to other scales as well. This is the Whirlpool galaxy, and you can see here the beautiful spiral arms. You see these blue dots in it, which are all regions like Orion, where young massive stars are illuminating their environment. If we look at this again in optical, in infrared eyes, in molecular eyes, then it looks very, very different. And then all of a sudden we see that this whole region, this whole interstellar medium is dominated by the emission from these paths. And then the message is very clear. It's shouting at us. It's basically saying, Gary, you naughty boy, why have you been focusing on this little teeny weeny small amount of optical radiation while you actually have the whole molecular universe at your command? Of course, when I was listening to Gary earlier in this conference, he was saying that he met Mike Seaton, and that Mike sort of introduced him into the atomic world, and Mike did that because he was a student of Eddington, and Eddington, of course, had a great disdain for molecules. He basically said that atoms are physics, but molecules is chemistry. And the last part, when he wrote that, he shuddered. And the reason is, of course, that you have to really understand molecules, and certainly in that time, that was not well done. And even in the time that we started thinking about photodissociation regions, that was not well appreciated, how complex this will be. And so I would like to give you a little bit of a tour through the remainder of this talk on through these molecular aspects of PDRs, particularly the role of these large molecules in PDRs. But I will come back to this atomic part to also pull in all those cloudy aficionados who like atoms. And this slide sort of summarizes a point that was being made by John so well, that the classical PDRs are these clouds illuminated by nearby young stars, like in Orion. We get this classic PDR on the surface, characterized by high density, high UV field. But actually, the whole interstellar medium is a PDR, because all of this gas is at, all the neutral interstellar medium is a PDR. It's all being illuminated by a UV field. All the chemistry and physics is very similar to the chemistry and physics in a dense PDR. The advantage, of course, of a classical PDR is that it's dominated, the size scales and the luminosities are such that we can easily study it, and so that has been the focus of much of our research. But actually, the results of studies on this side really apply to the real interstellar medium. And as we have seen just from looking at M51, this is really what the interstellar medium is all about. It's a giant PDR. Now, the pHs are tracers of the PDRs. They are very nice dyes, you can say, but they also play an important role. And that's sort of summarized in this slide, which shows that the physics of a PDR, the heating, is really dominated by small species. This is the heating rate plotted as a function of the size of the particle contributing. That's photoelectric heating rate. And this curve is placed in such a way that equal areas under this curve imply equal contributions to the total heating rate. And so half of the heating comes from PEHs, clusters of PEHs. Half of the heating comes from very, very small grains, and very large grains really do not matter too much. So it's very clear from looking at something like this that PEHs play an important role in the heating and the physics of PDRs. And that's sort of carried on in this slide. This is from Emma Baker's study. This shows the efficiency of the photoelectric heating as a function of the ionization parameter, slightly different from the ionization parameter that's being used in cloudy, but it's the same thing, that if this number is small, then you're mainly neutral. If this number is high, then you're mainly ionized. And when you're ionized, of course, photoelectric effect has much less effect. You don't contribute as much to the heating. And so you can see that the heating efficiency drops with increasing ionization parameter. And so this is the status of the field sort of in the early to mid-90s. And since that time, our thinking has progressed. And one of the things that we have realized is that there is an active photochemistry taking place in the interstellar medium of these large PEHs. And John talked about chemistry starting from small to big, so he started putting atoms together into larger structures, forming OH+, H2O+, SH+, and in protective environments of dense clouds. But there is also a different way to drive chemistry. So when you start by stars when they die, they inject much of their material back into the interstellar medium, and that's enriched in molecules, in dust, and when that is in the interstellar medium, get further processed by UV photons, and your PEHs may get broken down to smaller molecules and isomerized to structures like fullerenes. And if you want to study this, then one of the best ways to study this is in PDRs and photodissociation regions. This is the classical PDR, NGC 7023. You see here a cavity blown by this central star. This is the PDR front. There is a molecular cloud behind it, and the material is sort of flowing through this front into the cavity and then out into the interstellar medium. And when this area has been mapped by the IRS on Spitzer, and here are some of those spectra. You can see a nice spectrum fully dominated by PEH emission features, where you're sort of here. But when you get closer to the star, you can see these new bands popping up due to C60. And so you can see that there is a evolution. C60 comes up when you get close to the star. And you can actually make that quantitative. This is plots the abundance of PEHs as a function of distance to the star. So the star is over here and starts with about 7% of the elemental carbon in the form of PEHs. And when you get close to the star, that drops to about 2%. So PEHs are being destroyed in the strong UV radiation field of this star. And at the same time, we see C60, the abundance of C60 increase from about 10 to the minus 5 of the carbon to about 10 to the minus 4 of the carbon. And so while the PEH is being destroyed, C60 is being formed. And so this general scheme that is thought to be responsible for this is that you start with PEHs, and when you shine UV light on them, you rip off the weakest chain first, and those are the hydrogen atom. And so you convert these PEHs into graphene, and then from the graphene you go to flats, rings, chains, and eventually the atoms that and at the same time, during this process, you may also have some isomerization taking place to cages and to fullerenes. And so we mimic this in our laboratory studies. So here we have an ion trap. We store an ion in it. We raise it with UV, with photons from a strong laser. You can see this is HBC, hexabenzylchorinene. It's ionized. and when it's illuminated by this laser, you can see that you start to rip off the halogens until you get to the bare carbon cluster. Then when you increase the power of the laser, you can start to see that you start to lose C2 units. You start to break down the carbon skeleton. You make them smaller and smaller until you reach C32. That's sort of the last stable cage that you can have. And then you switch over to the chains. And so when you do this, you can actually also try to probe what the structure is of the species that you're forming. And here we compare some PEHs, photolysis of PEHs at 355 nanometers with that of the fullerenes. And with the fullerenes, it's very clear that you get these magic numbers. You get fragments which are more stable than the fragments around them. And that's a very clear pattern that you can use to identify what's happening. Here's C60, here's C70. You can see this magic number very clearly. When you reach C60, you can see that that's very, very stable here and dwarfs the surrounding peaks. PHs behave very similarly. They also show the same kind of magic numbers, and they show a similar kind of behavior. Here's the at slightly different wavelengths, 532 nanometers, and we picked that wavelength because at that wavelength C60, the fullerene does not break down. It does not absorb, and so therefore it is stable and stays at C60. You can see that C70, it starts to lose carbon atoms 2 at a time, and while it does that, it shrinks until it reaches C60, and then it is stable. It stays there. Now your C66H26, you lose the halogens, you start to make the carbon skeleton, but you can see that here too, you make a C60 component, which is very stable under these conditions. And so we think this is evidence that the fullerene, the graphene platelets that you make by stripping off the halogen isomerize to C60. There's a study done a slightly different way. This is a surface, and on this surface there are some graphene sheets which are going to be evolving under the irradiation of the electron microscope. So there's a little movie clip that I'm going to show, and just to guide you, because it's difficult to discern what really is going on, you will see that this graphene sheet will change, it will roll up and form this nice little soccer ball. And here it is driven by the electron irradiation, but we think a very similar process takes place in our experiments. And so here you can see that it is changing. I thought it was appropriate here in Mexico. When I showed this movie clip in Germany, actually the Germans were standing on their chairs shouting "Go!" Yeah, but it's the same process. You roll this up into a little ball, a soccer ball, and this is molecular dimensions, and it rolls on this surface. That the pH family is changing in these PDRs is also evident when we look at our, we studied this in the pH bands. This is again the reflection nebula NGC 7023. We're observing it here with SOFIA, with the forecast instrument, and the flight cam instrument. We're measuring the 11.2 and the 3.3 micron bands. Both are CH mode, very well separated in wavelengths, and so their relative strength is a good indication of the excitation of the species. And the excitation mainly depends on how large the species is. And so this is really a size indicator, and that's illustrated here. This is the relative intensity, the intensity ratio of 11.2/3.3 is a function of the number of carbon atoms running from about 20 to about 150. And these are different pHs which have been measured in the laboratory or calculated by DFT calculations. And these different bars here indicate different levels observed in this study, and they correspond to the contour levels here. And so you can see that on this prominent PDR front, the pHs are relatively small, and then when they move into the cavity, the star is somewhere over here, they start to be broken down, and the smallest ones disappear first. So you can see that the size of the pHs increases when the average size of the pHs increases when you go into this cavity. Sort of the power evolution that comes from this, the general scheme, is illustrated in this cartoon from Els Peters for slightly different objects. And you see 2023, but it's the same kind of structure. There's a star over here. Here's the molecular cloud. There's a PDR front. And deep in the cloud, the pHs are clustered. When they get exposed to the UV field from the star, these clusters will evaporate. They're very loosely bound by van der Waals forces. The structures that you have are fairly unstable. They get broken down to the most stable pHs, the so-called grandpas. And then once they pass this PDR front and approach the star, they get broken down. The small ones get destroyed, and you get this transformation into C60. Of course, this has implications for our understanding of PDRs, and I sort of illustrate that with this one curve here that shows the photoelectric efficiency as a function of the ionization parameter, and this is the curve that you would get if you have sort of an MRN distribution of pHs well into the molecular domain. But this is if you are really left with only a few very large pHs that are present, like if you only have grandpa present. I can see that behaves very different. I mean, the typical PDR is in this area of the parameter space, and so accounting for this will be important. Trying to understand the molecular physics and incorporating that into your models is a key aspect. This is another illustration of what could be important. This is the efficiency and normalized for different largest grains that are present, and you can see that it depends very much on the details of the power distribution in these regions to see what the actual heating rate is in these areas. And so it's very difficult to really get this from molecular studies in itself. We need to be guided here by observations, and we are getting these first observations already from Spitzer and with James Webb. It will be, of course, much more. What you also like to do is use your PDRs as sort of a laboratory to study the photoelectric heating as a function of the ionization parameter, and then use that to try to understand, for example, extrapolate to the diffuse interstellar medium, to diffuse clouds. And so this is the best data that was available some 10 years ago, and it shows the photoelectric efficiency as a function of the ionization parameter. And you can see, well, sort of, you know, if you squeeze your eyes, the models don't do too bad. But we have, of course, much better data, and we're getting much better data. And so this is one example. This is again taken from SOFIA. This is the upgrade study of the Orion B clouds around the horsehead. You can see it best here, the horsehead structure. And the contours here are the carbon plus emission. The colors are far infrared here, pHs, and here's CO. And you can see it traces very well, the carbon plus traces very well with the PARs, because they both trace PDRs, and not with the CO. Basically, all this emission comes from the CO dark gas that John was talking about in the previous talk. And then you can take the observed carbon plus intensity compared to the PAR intensity, and then you can get some sort of a relationship tried from a semi-empirical, trying to understand what the photoelectric heating is doing in this region, because the carbon plus is really the dominant coolant of this region, and the pHs are supposed to be involved in the heating. And this is this Orion B data. This is actually the Orion A data that was shown in John's slide. It's this data around the trapezium itself, the classical PDR. And this was done with Hi-Fi on Herschel, about 100 square arc minutes in 20 hours. We're going to map this whole region with upgrade on SOFIA. It's about a square degree in about 55 hours. And it will not only give us the radiative interaction, but also the dynamic interaction, because you can see this nice bubble here that has been blown by the stars in this region. I see that my time is running out, and so I have to satisfy some of the atomic aficionados. And so let me go to the largest species in space. The largest species are actually atoms, Rydberg atoms. And LOFAR has opened up the low-frequency sky to studies of radio recombination lines, and all of a sudden we can study these carbon radio recombination lines which come from the diffuse interstellar medium. Just as an example, I have here a study of the carbon radio recombination lines towards gas A in the 10 to 35 megahertz range. Optical depths that we can measure are of the order of 3 times 10 to the minus 3 with very, very good signal to noise. That's basically because of the power of stacking. We can stack a number of lines on top of each other and increase the signal to noise that way. We also see beta and gamma transitions, not just the alpha transitions. And we can use all of that data to analyze the physical conditions. This is a quantum number we see from about 250 all the way up to 600 in this. Actually, we go to n equals 1,000 in the low frequency range. These are the data points. You can see it's very well fitted by our models. That's all atomic physics, so it's easy to make these kind of models. And it's actually fairly accurately determined, because if you change the density by only a little bit, you can see you get very different fits to this. So you can do this to about 15% in terms of the electron density and the temperature. We're probing here actually the surface of a molecular cloud in the Perseus arm along the line of sight to Cas A. Here are these carbon radio recombination lines. These are now at 1 arc-minute resolution. This is the electron density at that same 1 arc-minute resolution. And you can compare it to, say, the OH emission absorption, OH absorption towards the same star, which traces the more diffuse, the translucent cloud that John was talking about. And here's the CO. And so you can see that we're tracing really this CO dark gas that we, and this is a typical diffuse translucent kind of environment. We can also get the cosmic ray ionization rate. Here are the one spectrum showing the different components, and the 2 components in the Perseus arm, 1 in the Orion arm. These are the carbon radio recombination lines. These are the hydrogen radio recombination lines. And you can just compare the 2, and you get a ionization rate of about 5 times 10 to the minus 17 per second. This is not in the diffuse medium, of course. This is in these molecular clouds where the ratio can be much, the ionization rate can be much lower. You can compare it to the H1. In this particular case, the H1 is actually self-absorbed, and so you only get a limit, saturated, and you only get a limit on the column, and that means that the abundance that you derive from this is really not that stringent. But in other directions where that's not the case, we can certainly get carbon abundances, and we can probably measure that throughout the galaxy. Our goal is to do a survey of the whole galactic plane, where we see these lines in absorption against the radiation from the galaxy itself. So this is synchrotron radiation of the galaxy. And you can see here's about 4 hours of integration, about 40 lines stacked, and you get a very nice detection here. It's shown here, the light here is the larger optical depths, and the contours here are the continuum emission. This is at a 1 degree pilot study. We have recently started a 10 arc-minute pilot study, and you can see here are the first results of it. I think this is the one that you really want to look at. This is a comparison of the spectrum for one of those 10 arc-minute beams against the H1. And you can see that we see this component, which therefore has to be cold neutral medium, and we don't see this component which we think is warm neutral medium, because the warm neutral medium will not be very bright in these lines. Then let me summarize, because Bob is getting very anxious now. Large molecules are very important if you want to understand the physics and chemistry of PDRs, if you want to understand the physics and chemistry of the interstellar medium. And this top-down chemistry is very interesting for a molecular aficionado like myself, but it also has direct implications for understanding of these regions. And the largest species in space are actually these single carbon atoms. You know, n equals 1,000 corresponds to an atom which is 100 microns in size. So it's really a very big atom. And together, these power studies, the carbon 158 micron lines, the carbon radio recombination lines, will give us a new view of PDRs and the interstellar medium. And if you think about it in those terms, then you can see that we're really living a very rich lifetime. There are so many different missions which all are going to contribute to bringing all of this data together. There's, of course, James Webb, which will go up in 2018, which studied the pH emission in PDRs. There's here Sophia. Sophia has, at this moment, has upgraded this carbon 158 micron line that it can study at much better sensitivity, much better mapping speed than was possible from HiFi. There is an instrument in phase A, Shasta, which is a 64-element heterodyne array geared towards the carbon plus line, and that will give you another factor of 10 increase in sensitivity. That will open up for studies of PDRs throughout the say 3 kiloparsecs. You can do all the bright regions of massive star formation. Here are these balloon surveys, which will do the galactic plane from the South Pole, and the first one mission is going up is going to be launched in December, the summer in the Antarctica. And Gusto is in the phase A study. Spica and Perspex are missions which are competing for the M5, and which both will be able to study the carbon plus emission line throughout the galaxy. And I already talked about LOFAR probing the carbon rate recombination lines. This is Ka, which will give you another factor of 10 or 100 increase in mapping speed and in sensitivity for studies of the radio recombination lines. And so it's very clear that we live in a golden age for astronomy. And when you live in a golden age, you can start to dream. And I'm dreaming of this carbon plus pH universe, where your carbon radio recombination lines, the carbon plus 158 micron surface, will give you the densities, the temperatures, the electron fraction, energy balance, carbon abundance, cosmic ionization rate of all the PDRs and all the diffuse clouds in the interstellar medium. Now, when you reach my age, you realize that you can have dreams. You realize that you will never see those dreams fulfilled. But your students will. Your students will see much more than whatever you will see. And I've shown you the missions that will bring this over the next 10, 20 years. But in the end, really, of course, depends also on how we teach our students and how we give them the tools and the understanding that they can analyze and interpret this data. And that's where I come back to Gary. As I said, many of my students have worked with Cloudy, have learned so much from it. And on behalf of all of these students, I say thank you, Gary.
Questions? Gary Furlan.
What a wonderful talk. One question we have in Cloudy, in the Orion bar, you can clearly see that the pHs disappear in the H+ region. And then there's strong pH emission. Then it disappears in the molecular region, probably because of self-shielding and extinction of the UV. But you have to assume something about how the pH abundance changes in the molecular gas, and that changes the electron density by an order of magnitude, whether there's pHs in the molecular gas or not for a given ionization rate. So what would you suggest as a prescription for how to carry the pHs along a ray into the molecular gas?
Well, my first suggestion would be to wait until this data is being analyzed on regions like the IC434, where you can actually resolve these regions. The problem is the Orion bar is, of course, it's very small scale. But I think in Orion B, we can follow these processes where the bar clusters evaporate, they form your pHs, they get ionized, and they get destroyed in the gas. You can also measure. You can measure the photoelectric heating rate. And if you do this for enough regions, and if you know what the electron densities is, because of these other studies I was pointing at, then all of a sudden you can make this a semi-empirical approach that you can build into cloudy, and you can give it to your molecular physicist friends, and they can play with it in the lab and try to understand what it says about the pHs, and you can play with it in cloudy and understand what it tells you about the structure of the interstellar medium.
Sylvan? And this will need to be the last question.
So let me ask the same simple question I was going to ask John, because I think it's irrelevant. What is the best current estimate for CO dark, the mass fraction of CO dark molecular gas in the Milky Way? In other words, should we worry about it? I mean, are we talking about tens of percent or less? Or is that a question
comparable amounts. I think comparable amounts to the CO molecular gas.
Okay, so it's a very large fraction.
It's a very large fraction. And trying to understand its relationship between the atomic gas and the translucent gas and the molecular gas, like say towards gas A, but in general in the interstellar medium, is a key question that we have to.
Would this fraction also go down in objects like ULARC, more extreme starbursts? Or is that the question that cannot be answered now?
Well, isn't that the question that we really would like to understand?
Yes. I would, yeah.
Yes, sure. and so I think we first have to sort out the issues and the physics of these processes in our own galaxy before we start to extrapolate it to a ULARC environment.
Great. Let's thank our speaker again. We're changing computers, and I know that Nick has carefully prepared things, but that does not always guarantee success. Our next speaker is Professor Nick Abel from the University of Cincinnati. Nick was a student of Gary Ferland's at the University of Kentucky, and no disrespect to Tom Trollin, probably knows more about the Orion Veil than the rest of us. Nick, you're on.
Well, thank you, Bob, very much. So there's I think a phrase in at least the United States that you never want to be the comedian that goes after Robin Williams. So to some degree, I feel like I'm doing that in duplicate with going after John Black and Xander Tielens. So I'll try to pull my weight as best as possible, which, as you can look at me, I tend to be pretty good at doing. So what you'll see here is that I'm going to do a more focused talk on the just one particular object as opposed to global properties of PDRs and the many wonderful objects we looked at in the last hour. And we're going to look at an object that really you can't see except for its effects on the background M42. So what I'm going to talk about here is Orion's Veil, which is the neutral layers of gas and dust that if you go from Earth to the trapezium cluster, that, in fact, if you go anywhere from Earth towards the Orion Nebula, you're eventually going to be smacked by two neutral layers of gas at fairly close to the Orion environment, but in front of the trapezium stars. And you can see that here from if I show you what the Orion Nebula looks like if you remove the veil, the cloud of gas and dust in front of trapezium, you can start to see the extra filaments that I believe Bob was talking about yesterday. You can see I believe you could also see this in John's presentation with the C2 as well. You can see the true shape and nature of the veil. So I want to talk about the physical conditions and that object, and you can see here the litany of co-presenters and people who we've collaborated with over the years, over this about decade or so, collaboration on trying to understand the physical characteristics of the veil. Now, the veil is important for a couple of reasons. One is that the distance of the veil clouds between from the trapezium to wherever this veil is located is one of the more uncertain geometrical entities with the Orion complex. And I have a is/was here. So I'm going to highlight the was part because in this presentation I'll show you how we now have, as a result of computational modeling combined with the wealth of observations we have of the veil, now you're going to see that we have a much tighter constraint on how far away these neutral layers are before you get smacked by them. So the wealth of observational data we have in the veil, from the optical to the radio to the ultraviolet, and you can see a lot of absorption lines material in this presentation, allows us to really make a well-refined model of this object. So we're going to take one object and try to realize the dream of the previous presentation, and just for one of the many objects in the Milky Way, try to understand the temperature, energy balance, and the wealth of information that we have for the observational properties of the veil. And I'll go over that in this presentation. Now, one of the observational constraints we have is the amount of molecular, we have observations of molecular hydrogen in the veil, which, as I'm going to show here in this presentation, is at about the same level that John had mentioned as being the threshold, that sharp transition, about 10 to 14 H2 column density. That's about the column density of the veil. So studying the veil basically allows you a way to study kind of that sharp transition from atomic to molecular gas. Now, I would be remiss if I didn't try to sell a couple of my friends' books while I'm here. So, see here if I can get this laser pointer to work once I'm shooting it at me. So, different button. Here we go. So now, if the translation for this says something inappropriate, I apologize and blame Google Translate. That's why I did a direct copy.
A correction from the chair. You can get it on Amazon for like $1.25. Because of the libraries sell them back because they're not circulating.
Well, I would prefer to get Bob as much profit as possible. So if anybody wants to make a charitable donation. Now, I would be also remiss if I didn't also try to hawk my good friend and PhD advisor Gary Ferland's book as well. So I have a copy here of this. It's not for sale because it's signed by the author. But if you want to go online and notice that his book is 3 times more costly than Bob's, Gary has expensive tastes. So if you want to help out his various needs, and please feel free to wherever the button's out. Buy now. So as I continue here, now I want to talk about the wealth of observational data, the important and that's really what makes the veil unique, is we have so much data associated with it. It makes for a very good test of chemical models, of how we're going to try to apply calculations to understanding reality. So just like John said, there's basically, you can think of galaxies, ensembles of Orions. And so by being able to apply this for a cleaner test where we have all this observational data, it gives us more confidence that we can apply our computational models to more to regions where there's less available observational data. So one of the things we can compute is that since the background H2 region is a very strong radio emitter, and we also have this data for H alpha, H beta towards in the nebula, what we can do is we can use theory to calculate how much H alpha, H beta should we see, and then compare that to one of the radio frequency intensities, and then from there, based on what we observe versus what should be emitted, we can then come up with a map of how much extinction is across this neutral layer. So although we can't see it, we see its effects in extinction, we can map that extinction. And so what you see here, the bigger the numbers on this map correspond to, here's the dark bay, you can see the bigger numbers, that makes sense. And towards theta 1c, and the brightest of trapezium stars, which is going to be the source of ionization for the veil here and for the background Orion Nebula, obviously. But if you look just towards the sight line, the visual extinction is about 1.6 magnitudes. So we can compute the extinction, and while the veil is a very large object itself, for most of this talk, I'm going to focus on just this one sight line, asking what's the physical conditions along a ray through the veil going right towards the trapezium stars. I believe Tom will talk a little bit more about the global properties of the veil in a later talk. Now, once we have the extinction, we also have the total H1 column density. Now, ignore all these squiggles. That's just unprocessed STIS data. I just wanted to basically show the whopping Lyman alpha absorption line here. And from that, you could also see this with IUE. In both instruments, when you calculate the H1 column density, come out to about the same number, about 4.85 times 10 to the 21 is the total H1 column density trying to go through the veil layers towards the trapezium star. Once we have that, then we can come up with a dust-to-gas ratio, which is about 60% of the interstellar medium. So there's less dust per gas. And in addition to that, we can come up with the ratio, because we know the reddening of the trapezium stars. Based on the ratio of the visual extinction to reddening, we get an R value which parameterizes the, among other things, the dust grain size distribution. We get about 5, which is also higher than the ISM value. So this tells us overall that the veil is not very efficient at extinguishing the ultraviolet radiation. So the grain size is going to be weighted towards larger grains. Now, we also have a map of the magnetic field because of the background radiation, the 21 centimeter. When it tries to go through the H1, gets absorbed. So we have maps from, and Bob can tell, Tom can tell you a lot more about the magnetic properties of the veil at a later talk. In fact, to publicize, make sure one of Tom's favorites statements here, stealing a little bit from the political scene. Tom will tell you all about magnetic fields in a later talk. I do want to point out towards the exact sight line of the trapezium cluster, the line of sight magnetic field is about 50 microgauss. Now, we also have from that, since we can observe H1 21 centimeter in absorption, we can come up with optical depth profiles for the veil. So we can see some velocity profiles I'll show you here in a second. That's going to be important because if we can come up with an integrated line profile, we can come up with an equation which relates the spin temperature to the H1 column density. So we're building a database of knowledge for the veil that we can then apply a chemical calculation to. So here's that line profile. Now, when I say the veil layer, I really make sure I pluralize that, veil layers, because there's, in 21 centimeters, there's 2 clear velocity components. Now, based on what preference you have for the velocities, either heliocentric or local standard rest, as Bob mentioned, subtract 18.1 to get from one to the other. What I want to point out is the 2 components. One's a narrow component, component A, and best way maybe to memorize this is you can have component B as the broad component. So the letters help with that. So when we fit profiles to this, we can come up with a, now notice this is, while this looks like it's going that way, so you might think of that as emission, this is an optical depth profile, so then the higher up, the more absorption you have. So then we can integrate those profiles and get an equation for each component relating the spin temperature, the H1, that should be H1 column density for each one of those components. Now, since we have line profiles, we can also talk about the velocity widths. And that can give us constraints on the kinetic temperature. If we assume that all the broadening was due to thermal broadening, not a very good approximation, but at least gives us upper limits on what the temperature can be. For the narrow component, we have 87 Kelvin, and for the broader component, the temperature can be a little bit higher. So any model we construct has to make sure the temperature is below that. Now, for a while, we only we knew about the H2 in the veil is that there was a upper limit to it. And so what you're looking at here is a paper from that very important paper from the 70s that plots for the reddening of a star, how much H2 column density you have. It makes sense that the more reddening you have, the thicker, the more shielding, the more H2 you should have. Now, the reddening towards the trapezium stars is about 0.3, which, when you then compare to this graph, should give you a column density typically about 10 to 20. However, the veil on this diagram is right there. So the molecular hydrogen content in the veil is much lower than we expect, we can start to reason out that that's probably due to the lack of effective UV shielding. But also, what it means is that this must not be a Hamming field of 1, not a standard G0, but it's probably much closer to the UV source, the trapezium stars, to produce a sufficient photoassociation. Now, we do have molecular hydrogen observations now, and that's because with STIS, we applied for time for on HST to detect, since there wasn't much molecular hydrogen, we know there's an upper limit. We needed very sensitive, about solenoids of 100 or so, observations of trying to get what we knew was going to be very weak absorption features in molecular hydrogen. So what you see here, this series of profiles, we can see the absorption. Sometimes it's a couple percent, sometimes it's around about 10%. It's all, however, very low optical depth, which means we are pretty much on the linear part of curve of growth. We can extract column densities from this. Also, I want to point out here is that visually, almost every molecular hydrogen component is associated with the velocity of component B. There's not much absorption in the 23 kilometer per second velocity component associated with A. So it appears that the molecular hydrogen we're observing here is just associated with one of the clouds along the line of sight, the broader component B. And then once we do, and this shows that as well, the velocities here shown are all in the 18, 19 category, except for 2. But for the most part, these absorption features are associated with component B. So there's a lot more molecular hydrogen in component B than component A. So the STIS data tells us that. And we can then turn this into an H2 excitation diagram. So what you're looking at here are column densities for highly excited states of H2. So we're not talking about ground state. This is not going to be used for a temperature indicator by any means. These are ultraviolet pumped molecular hydrogen. And this excitation diagram where we take the column density divided by the statistical weight versus the temperature. Any model that tries to accurately reproduce the physical conditions of component B has to be able to reproduce this excitation diagram. So you can continue to see here that we have more and more data. We have molecular hydrogen data. We have extinction data. We know something about the dust along this line of sight. We don't have to assume ISM properties. We can build grain size distribution and amount of extinction based on observation. We also have observations of carbon-1. Now, with STIS, what allows us to measure the column density in the individual populations of the 0, 1, and 2 J levels. And for those FIR aficionados, that would also correspond to the transitions leading to 370 to 610 micron emission. So we can observe the level populations of those states. And this, because it's going to be sampling those level populations, should to some degree be sensitive to thermal pressure, density, temperature combination. So if we could just apply a model to get this aspect correct, then we could come up with a measure of the thermal pressure from each component. We have the magnetic field, and we can start to compare the various energy balances in the veil. So we take that data and we observe the carbon absorption for each of the 2 velocity components. And you can see at the very bottom here, the C1 double star, which again symbolizes the various J levels, that if I go to the figure on the previous slide, there's not a whole lot of absorption at about where component A is at, as opposed to C1 and C1 star, which has some absorption at that location. So C1 double star for the narrow component A, the one at the velocity of 23.5 or so, has a much larger error associated with it, and everything else is a pretty tight constraint on the observed carbon column density, which again applies tight constraints for any model trying to reproduce the conditions. Now, we don't have, with Lyman alpha, you can see there's no way we're getting any kind of velocity resolution for the H1 column density, but we did figure out a way to divide up the H1 column density into individual components, and that's because we can observe a lot of other species that should correlate directly with the amount of H1. Krypton-1, copper, magnesium, oxygen, all of these, we saw the same line profile shape as a 21 centimeter. and since they should follow and track the abundance of molecular hydrogen, atomic hydrogen, what we observed is that for each of these species, krypton, oxygen, copper, we had about 2/3 to 1/3 ratio. About 2/3 of that column density was in component B, 1/3 was in component A. So when we divide that out, we can then say we can take our 4.8 10 to the 21 total H1 column density and then associate 2/3 of that with component B, associate 1/3 of that with component A. So, and now there's a little bit of an error associated with that from the error in the Lyman alpha column density derived. But once we have that, and we have the optical depth integrated, we can then come up with the spin temperature for each component. Again, places a constraint on the model also allows us to test whether when we get a temperature from the model, does that compare with the spin temperature? Are things in equilibrium? Is there a difference between one temperature and the other? Now, to list all this, let's make sure there we go. We have all this information. We have extinction, abundances, dust properties. The trapezium stars have been well studied. We have a pretty good idea of their solar radiation field. So we have constraints on H2, temperature, spin temperature. All of this data we have at our disposal. So from here, we want to take all this data and see if we can construct a model that reproduces that with the goal of extracting out a density and a temperature for each component, which then gives us a thermal pressure, which we can then compare to magnetic pressure, turbulent pressure, study the energetics of the environment. And to do that, as you might not be surprised, we will use cloudy. So we're going to see a time evolution of cloudy as we go along. Here's cloudy at 10 years old. So you can see a birthday celebration for cloudy right there. So back, I guess, in the earlier days of the history of the code. And you can see what we're studying here. We want to know the distance of the components to the trapezium. We want to know the investigation of energy balance. We want to test the ability of a model to reproduce observations. And we will also want to come up with that model that extracts out the molecular hydrogen content and compare it to the very low what we observe. So this is almost a pure atomic hydrogen gas with the molecular hydrogen about a millionth or 10 millionth or so. Oh, and so there's cloudy. Continue the time evolution. Here's Cloudy's 20th birthday party, which is a little disconcerting in that the legal drinking age is 21, so Cloudy's probably feeling a little bit left out here. But the calculation we're going to use comes from Cloudy and incorporates like the hydrogen. We're going to take all this observational data set and try to reproduce the observations. So to do that, all the grain PDR physics that's been well worked on the last 10, 15 years or so. For instance, the grain model from Weingarten-Drain and put it by Peter Van Hoff, which Peter, besides being an excellent physicist, is also very good at not having his image on the internet. So I had to therefore modify. And so there's with Peter, his head is an interstellar dust grain, and then photo not available. So we have a stellar continuum model, which comes from a paper by Will Henney that has reproduces a lot of the emission characteristics. And so we've inputted that. And as you might guess, there's an image of Will, which I've gotten permission to use by him. We have a model for complete treatment of H2 excitation, which is required to get the analysis with the excitation diagram. And that was the PhD work of Gargi Shaw, which you can see here in a happier moment, getting rabbit ears from her PhD advisor, Gary Ferlin. And eventually what you'll need here is that with all this data, we have very few constraints, and we need somebody to run those models, and for that, there's me. So the camera loses about 100 pounds and gains a chiseled chin. So here's the results. The shaded region, so we ran a model that varied the distance away of cloud, varied the density. This is a constant density model. And the shaded regions is what we observe for component A. We have different stopping criteria for each individual component because we know the total H1 column density, or have a good estimate of it. So here's the shaded regions, and then the temperature for component A. Remember, that's the narrow one. Here's the calculated average temperature. Also on the right axis here, you'll see G0 for you PDR aficionados who'd prefer to see this in G naught as opposed to distance. So we can eliminate this part of the parameter space for component A because its temperature is too high. It's greater than allowed. Now we put all this together. What you see here are 3 lines representing the central value for the observed C1 column densities. And you can see they cross quite well in this narrow area. When the referee looked at this, he was quite impressed by how well this model agreed with the theory. I was afraid the next line was going to be, I don't believe this. So happily, that was not the case. So when we put here a little triangle representing the observational compare with model, it agrees very well. For about a density of 250, a G naught of 300, it tells us the distance away, which from there, we can now get comparisons to magnetic and thermal energy and pressure. And what you can see here is that since the ratio is so small in the magnetic parts in the denominator, the magnetic energy and pressure dominates over turbulence, dominates over thermal pressure. This is a magnetically dominated component, so by no means in any kind of energy equipartition. For component B, we stop at a bigger column density. You can see the constraints here. So you might notice that the H2 is a little bit more moved in. That's because the bigger column density means that we have a larger region of the parameter space that exceeds the Copernicus limit. Temperature doesn't help any because the entire parameter space has a temperature less than 320. Now, when we compare to observation, we have, here again, the central values for the observed. There is a sizable region. It's not as clear. It's not almost to a point. This whole region would, within a sigma, be able to reproduce the C1. But we have one extra constraint for component B. We have the excitation diagram from molecular hydrogen. And previous estimates of the distance of component B is 0.4 parsecs, which would put it right about here. So this model would agree with that distance right about there for the C1. But what we want to do now is say, all right, with the extra observational constraint of the molecular hydrogen, what will this tell us? Will molecular hydrogen agree with that 0.4 parsecs, or does something else have to be reasoned out? Here in blue is the predicted cloudy H2 excitation diagram at 0.4 parsecs compared to the red, which is the observation. And what you see from here is that it's not very good agreement. So what we then did from there is like, all right, if this 0.4 parsec estimate, let's remove that as a constraint and just ask the question, which model best reproduces the H2 excitation diagram? And what I'll show you there is this one. If I toggle back and forth, I think the visual should make clear that one has a much better agreement with observation than the other. Now, not perfect, but the vast majority of these column densities are within 0.1 dex of the observed. And this model corresponds to this density, G naught of 800, and a distance of 2 parsecs 5 times farther away. And if you want to ask, does this model agree with the C1 data? It does. That triangle represents the best H2XI diagram fit, which also agrees to within a sigma of the C1 column densities. Now, without the machinery of the molecular hydrogen microphysics in cloudy, we wouldn't have been able to do this extra observational test. We would have also concluded the 0.4 parsec distance sure had a good fit to everything else. But the extra constraint and the detailed model in cloudy allows us to compute molecular hydrogen column densities, compare them to reality, and we get a very good fit here. We get a distance, a density. We can then do temperature and pressure analysis. Here's putting it all together from component B. The ratio is a little bit larger. As you can't really say equipartition, but you can't really say it's completely dominated by the magnetic field. We have all this data. You can see here where it comes from, a mixture of models and observations. And the last thing I want to say here to summarize is that I think it's safe to say without Bob, Tom, and in particular without Gary's guidance and patience through the years, I wouldn't be here where I am today. So I would like to say, in agreement with Xander Tielens, thanks for everything, Gary. And right here you see Gargi, Gary, and myself. Thank you very much.
We have time for a few questions.
So one of the curious things about what you were talking about was the an unusual fraction of the grain mass being in larger grains, dust grains. Do you have any idea why that is? I mean, is there grain growth, or is are the small grains just being extracted somehow?
It's my impression that probably the radiation field is probably destroying the smaller grains. And so it's very close to the trapezium stars, so it's strongly affected by the Orion radiation field. One of the things to notice in that is the two velocity components, based on their velocities, they're actually moving towards each other. So at some point in the future, component A and component B will be component AB. So there's probably either radiation field or some kind of dynamics has probably destroyed the smaller grain sizes.
Thank you.
Will Hinney?
Thanks, Nick. That was a great talk. I was very gratified to see that you now get a much further distance for the veil.
Me too.
With respect to the Van der Werf, because it now looks consistent with the general shape you see of the extended Orion Nebula. If you imagine that what you see in the PAHs around the side was sort of rotated round, and that would also imply a distance of about 2 parsecs along the line of sight.
And Tom will talk about in his talk a bit later how it also agrees with some of the magnetic field balance.
So can you comment on what might have gone wrong with the Van der Werf estimate of a smaller distance?
Bob, Bob was on a previous paper with Van der Werf and did a lot of the analysis to also after we had noticed that the molecular hydrogen agrees at a much larger distance, we then went back to the kinematic argument. I would probably punt here to Bob. Would you have a reason why we would reject
Nothing
that?
that you can't say. I wasn't really following it because I was...
Oh, sorry. The kinematic argument for the larger, the smaller 0.4 parsec distance being rejected. I know we had a lot of discussion about that as we developed this paper. So why are we rejecting the 0.4 kinematic argument for the Van der Werf paper?
Maybe we should take this to the discussion.
My main, I guess, contribution to this was that noticing the molecular hydrogen discrepancy and then figuring out just based on the UV, we then went back kind of afterwards to see if the 0.4 parsecs was, how rigorous that was. And I do know in the end we decided that there were a lot of assumptions that we could, that had a lot of hand waviness, I would say, to it, that we could then make more rigorous with the UV. So we can talk later if you like. So.
Manuel?
Yes. You mentioned that the total to selective extinction is 5, is high. Can you say something about where the grains are, if they are inside the H2 region and the first veil, in the second veil, and the sizes of the grains?
Not component by component.
Okay.
If we assume the constant gas to dust ratio, then we can talk about how much AV is due to each one. That would assume a uniform mixture.
Okay, let's thank Nick again. Our next speaker is Annika Franeck from the University of Cologne. You see her subject, and she is eager and a little anxious to present it to you.
Okay, thank you very much for the introduction. Welcome again, and also thank you for the organizers for giving me the possibility to talk today. I'm in the University of Cologne, and I work with Professor Stefanie Weich, and we're studying the evolution of a multi-phase interstellar medium with numerical methods. That means we have a setup, a simulation setup with a box size of 0.5 kiloparsec in X and Y direction and elongated in 10 kiloparsec, and there we set up an initial gas surface, a gas disk, so really just a piece of the galactic disk, and there we study how this evolves with time. This is part of the SILK project. SILK stands for Simulating the Life Cycle of Molecular Clouds, And then this is a collaboration between different universities in Germany and between Prague with Richard Wünsch and Cardiff with Paul Clark. My part in this project is then to make those simulations comparable with the observations. And this I do by carrying out C2 synthetic emission maps of our pieces of a simulated galactic disk. So I don't use Cloudy for those things, but my connection to this is to use some emission lines. So first I want to tell you some about the setup that we use, and then the second part then what we do actually with the synthetic emission maps. So as I said, we have an elongated box. We set up in there a gas disk with a surface density about 10 solar masses per square parsec. We also include a simplified chemical network with different species of hydrogen and carbon. And then we see how this disk evolves if we have the influence of self-gravity, heating and cooling. And what we don't treat in those simulations I show you today are the individual stars. But we have to take them somehow into account. So what we also do, we have an external stellar gravitational potential to keep the gas within the disk. And we have an internal interstellar radiation field. And we need some feedback processes. So we know the gas surface density of the gas. According to the Kennicutt-Schmidt relation, we can calculate how many stars do we expect to form. And every hundreds will explode in a supernova. So for gas surface density about 10 solar masses per square parsec, we end up with a supernova rate about 15 supernova per megayear. And what we can change now between the different simulations is the positions of the supernovae. For example, we can correlate them with the dense gas clouds. This is what we call peak position, and then everything explodes just there. Or we can place the supernova randomly. That means that some of them will explode in the dense gas region and most of them in the dilute gas. And the probability to set such a supernova is like a Gaussian distribution. The highest probability you have in the midplane itself, and then Gaussian distributed above and around. And the simulations I will show you now how they, or I will concentrate today, have a randomly distributed supernova distribution, and they look like this. We see here in a moment, yes, now, different slices of the density and temperature. We have the column density and different chemical species like ionized atomic and molecular hydrogen, carbon monoxide. We see the supernova explosions that heat the gas and that form an outflowing component. You can really see it good here in the atomic hydrogen. And we have components in the midplane, the molecular ones, so they form us the molecular clouds, like molecular hydrogen and carbon monoxide. And here are some components of molecular hydrogen we can't see in the CO emission. So these are the simulations I'm working with and my analysis is built on. And now I'm interested in how they look like if you could observe them in the C2 line emission. So C2 line is a fine structure emission from the carbon ions at 158 microns. And it's the main coolant in the ISM. You can see it as a bright line, and you can see it from different phases in the ISM. You don't need much energy to ionize carbon atoms to ions. So this is why you can see it from the cold molecular phases, and you need a lot of energy to get carbon ions to a higher ionization state. And this is why you see the C2 line emission still from warm and ionized phases. So people would like to use observations of the C2 line emission in order to study the CO dark molecular hydrogen, and also to learn about the star formation rate in galaxies. But to understand those questions, one has to go one step back and understand from which regions of the ISM you actually see your C2 line emission that comes from. And this is where we hopefully can help with our simulations. So we don't have telescope, we have a radiative transfer code. We use RedMC3D. And to make it work, we have to make some assumptions for our calculations. And we assume that we have a non-local thermal equilibrium. That means that we need collisions with other particles to populate the levels of the carbon ions. And we take as collisional partners molecular hydrogen, atomic hydrogen, and electrons. So the number densities of our different species, now we have hydrogen species, electron, and carbon ions, we get more or less from the code, so we have to do some post-processing. Then we get collisional rates from the databases itself, and the temperature and the velocity of the gas we get again from the simulation. RedMC then looks along every line of sight, how much emission do we get? So how much is emitted, what is absorbed, and then we get a signal for every line of sight, so for every point that you can see here. And if we make this calculation and integrate over the velocity, then we end up with synthetic emission maps that look like this. These are for the simulation I showed you some minutes before. We have different time steps. We see the intensity on logarithmic scales in different units. You can have a look from the side, from the top. We see a really strong signal from the midplane itself, and we see a faint emission of outflowing gas, which expands with time. Now, we want to analyze those simulations concerning the origin of the emission and its distribution. So for the origin, we are interested in to find out from which temperature phases of the ISM the emission comes from. So what we do is we cut our simulation box. We take, for example, here only gas into account up to a certain temperature. We make this radiative transfer simulation and see how much of the total intensity we actually get from those cutted boxes. So if we cut at 100 Kelvin, so only take the cold gas into account, then we already get an intensity of the total one about 80%. And we have a second contribution to the C2 line emission from the neutral gas phase, here between 4,000 and 10,000 Kelvin. This happens here. And concerning the distribution, we make profiles. Here's the set direction. We average the intensity for every set position and plot this in such a diagram. Here we can see it on logarithmic scale, and what we could also see from the further analysis, everything is dominated from the peak, from the molecular gas, from this contribution, and this makes two thin peaks from the midplane. And this, what you can see here, is a really faint emission in the background, but it still has a shape, and this is influenced by the supernova position, this shape, what we can see here. So now we wanted to measure this distribution somehow, and we found in literature that you can measure it quite easily if you assume a Gaussian function and fit this Gaussian to the different components that you can find. Then you have to set note here in the Gaussian function itself. This is what you call a scale height. So we did this. We have two components from the midplane. We have one extended component, and then we find scale heights about 5 or 10 parsec for those midplane components, and one for the extended one. So you might remember that I wanted to compare this with observations as well. So let's see what they find. This is a study from Belusami and Langer, 2014. They had got C+ data. They measured the C2 line emission in the Milky Way, averaged over everything, and got profiles that look like this. And then they distinguished between the different phases by ancillary lines to see whether it comes from dense region or the H1 and warm ionized medium. And they find a faint emission here correlated from the C2 line emission with H1 or warm ionized medium. And this has a scale height about 140 parsec. So we don't get the same number directly, but I would say it's somehow comparable. And then they look at the dense gas, and they find C2 line emission from the dense gas has a scale height about 55 parsec. And if we compare this with our simulations, we see this does not fit that much. And this is because in our simulation, all the molecular clouds are aligned in one thin disk. And this is not what we see when we look in the Milky Way, for example. There, the distribution of molecular clouds is larger. And this is why they end up with a larger scale height here, and we don't, because our model right now does not represent this feature. And the second point here is that they averaged over everything. So over the whole galaxy. And what we do is we actually take just a tiny little box of a galactic plane. So this is not directly comparable. So what we also would like to do is to compare those simulations, so local simulations, with local observations in the C2 line emission. Those so far don't exist, but they exist for other traces. And there's the work also done in Cologne by Christian Glück in his PhD thesis, and he analyzed how the carbon monoxide lines, these are the colored ones, and the atomic carbon lines look like in the profiles if we just have a look in a local surrounding. And if you look on those profiles, you can clearly see that they are not Gaussian. They are right complex. So we think that on local scales, the profiles look like quite different. And if you measure the scale height of one contribution here from just one peak, you end up with the scale height about 10 parsec again. And this is somehow comparable again with our simulations. So to conclude, we study the evolution of a multi-phase ISM in our simulations, and then we carry out synthetic C2 emission maps in order to compare those simulations with the observations. We found that the C2 line emission traces the cold and the neutral gas phase. They are distributed on different scales. We have a main contribution from the cold gas on a very small scale, about 10 parsec, and we have a contribution from the neutral gas. This gives us a faint emission on larger scales. And overall, the shape of the profiles are influenced by the supernova distribution that we set in. And with that, I thank you very much, and you're welcome to ask questions.
Are there questions? Yes, they're in the middle.
If you go back just one slide, kind of a tangential question, but it's interesting how asymmetric it is on the left side versus the right side. Is there an idea as to why that is so much side left?
Yeah, well, Christian Glück also measured how much this offset is, and then he made different boxes. So what he had data, he had velocity information, so he could disentangle from which region of the galactic plane the emission comes from. Then he binds it together, and then you see the distance here from the sun or from the galactic center. And you have some warp in this galactic plane itself. And he found that the offset position you have here follows quite well this warp, what is found in literature. So this is what he found there.
Interesting, thank you.
You're welcome.
Thank you very much. We are adjourned for coffee. We will resume promptly at 11:30, and you won't want to miss it.